with all of that, when we put things together, we now have our global matrix vector equations. Right? And they are the following. C, T, K bar, D bar equals C, T, F internal plus C, T, F, T bar. Okay? What's the last step we need to take? Dirichlet boundary conditions, right? Okay? And in doing that, we need to account for the fact that our K bar, I'll probably do without that arrow. What are the dimensions of our K bar matrix? Right? They are number of nodes times NSD minus ND, right, where the ND corresponds to ND is the total number of Dirichlet degrees of freedom, total number of degrees of freedom where the Dirichlet boundary conditions are specified, right? And this could be, this could draw maybe the one direction on some node, the two direction on some other node, and the three direction on yet another node, right? When we sum this up, we get 3, right? So then in that case, ND would be 3. Okay. So this times number of nodes in the problem times NSD. Right, so K bar, these are the dimensions of our K bar matrix. Okay. Right, okay, so clearly K bar is a rectangular matrix, right? And what we need to account for is the fact that when we look at the C transpose vector here, right, multiplying K bar, right, and here we have our global D bar vector, right. Let's suppose that now when I label the degrees of freedom for the D bar vector, right, that is D bar 1, 1, D bar 1, 2, D bar 1, 3. Okay. Now let me suppose that some global degree of freedom, right? So let's suppose D bar A1, D bar B2, and D bar C3. Okay, let's suppose that these global degrees of freedom are known Dirichlet boundary conditions. Okay, what this says is that D bar A1 is known. I'm not going to write D bar A2 and D bar A3 because those are not specified, right? Okay. Well, actually, let me write them and specify and sort of mark out the ones that are known. since I've run out of room here, let me just say that d bar, let me just get rid of d bar C3. Okay, so those are the ones that are known. Okay, so d bar A1 and d bar B2 are two known Dirichlet boundary conditions, right? And there will be more, of course, in this sort of problem. Okay, so that means that that degree of freedom is known and that degree of freedom is known. Okay, right? And when we carry out this matrix vector product, we know that this entire column right, and another one right, are going to be known. Okay, so for the way we had numbered it previously, this column is what I would call the k bar. Let me see. The column number here is the following. NSD times A, right, where A is the global node number, right, plus 1, right, because it corresponds to d bar A1, right, the one coordinate direction of global node number A. Okay, and this column likewise is k bar column number NSD times B plus 2, right? Right, this is the column. Okay, so since d bar A1 and d bar B2 are known, we do just what we've done before, which is to account for the fact that that these columns multiplied by those known degrees of freedom can be moved to the right hand side. Okay, so we do that, right, and then we are left with a reduced system C transpose K D equals C transpose F internal plus F T bar, right, minus d bar A1, which is a scalar degree of freedom, multiplying the column that we identified on the previous slide, k bar NSD times A for the global node number plus 1 minus d bar B2 scalar degree of freedom multiplying the column number k bar NSD times global node number B plus 2. Okay, and as we've been doing in previous problems, that is our final F vector. Okay, so what this implies for us then is C transpose KD minus F equals 0, right? And the degrees of freedom, the dimensions of this K matrix now, it's square, right? Because we've got rid of all the Dirichlet degrees of freedom which were known and moved them to the right hand side. Okay, so K finally is number of nodes times NSD minus the total number of degrees of freedom that had Dirichlet conditions specified on them square. Okay, that is the size, those are the dimensions of k bar. Now, of course, we invoke our weighting function condition that our weak form, our finite dimensional weak form, must hold for all weighting functions in the appropriate space, And the fact that it must hold for all weighting functions in the appropriate space is enforced here by the requirement that this matrix vector equation that we have as the last line of the slide must hold for all C vectors belonging to a Euclidean space of dimension number of nodes times number of spatial dimensions minus nd. Okay, which implies for us finally that we get back the same matrix vector form of the equations we know, kd equals f. Right, and we solve this for d, which will give us our global displacement vector. Okay, I should make one remark here that since we are talking of d being defined as k inverse f, right, under what conditions does this solution exist? Okay, solution exists, or there exists a solution D if our K matrix is positive, is invertible, of course. Right? Under what conditions is it invertible? What can you think of what it is that guarantees invertibility of that matrix? It turns out that for the 3D elasticity problem, K is positive definite. What conditions make K positive definite? One of the things that makes it positive definite is because our elasticity tensor C is positive definite. Is there any other condition? Yeah, if you have some experience with these types of methods and with solving linear systems of equations, you will probably recognize that it has something to do with our boundary conditions as well. Right? We need to have enough Dirichlet boundary conditions to eliminate what are sometimes called rigid body modes in the context of elasticity. Okay? So K is positive definite since C is positive definite, and if the Dirichlet boundary conditions eliminate rigid body modes. Okay? And the question of how to do that is a little more involved, which we won't really get into here at this point. All right. At this point, we are actually done with our treatment of 3D linearized elasticity. This was our example of a vector problem, and we'll end this segment and this unit here. When we come back, we will move on to a wholly new class of problems.